This is Physics 104A homework for Porterville College, Chapter 7. Starting with number 13, we're finding the potential energy of a 70 kilogram hiker. Take the zero of potential energy at sea level. I've written it out in terms of delta U, or change in potential energy, and really that's difference in potential energy above zero. So we can take these answers to be the potential energy. So delta U is mg times delta y. The potential energy is mass 70 kilograms times 9.8 newtons per kilogram times whatever the height above zero is. In the case of part A, it's plus 1900 meters. In the case of part B, it's negative 86 meters. So answer for part A is 1.3 times 10 to the 6th joules, and B is negative 5.9 times 10 to the 4th joules. Number 22 is a conservation of energy problem, a 35,000 kilogram boxcar moving at speed, stopped by a spring-loaded bumper mounted at the end of the level track. It gives the spring constant 2.8 times 10 to the 6 newtons per meter. How far does the spring compress in stopping the boxcar? All right, let's set it up as energy at 1. This is when the boxcar is speeding. And number 2, when it's fully compressed. We'll break down energy as U1 plus K1 equals U1 plus K2. And let's immediately get rid of the things that go to zero. So in the case of when it's speeding, it has no potential energy. We'll make that go to zero. And when the spring is fully compressed, K2 goes to zero. So we've reduced it down to the kinetic energy while it's speeding equals the potential energy while the spring is fully compressed. That becomes 1/2 mv squared equals 1/2 kx squared. Question is asking how far does it compress? X is the compression. So when you solve that algebraically, it's x equals plus or minus v times the square root of mass over k. Now the plus or minus, it's actually going to be the minus because that just means compression. So when we plug in the numbers, we have the speed, 7.5 meters per second. Plug in the values given in the problem, and we get negative 0.839 meters. For the final answer, I've gotten rid of the negative sign. We understand that it's being compressed, so I'll just give that as the absolute value of 0.84 meters. Number 23. Another conservation of energy problem. The launching apparatus has room for a spring that can be compressed 14 centimeters. The rocket's mass is given. If the rocket is to reach an altitude of 35 meters, what should you specify for the spring constant? All right, so energy at 1 equals energy at 2. Our state 1 is going to be when the spring is fully compressed, 1/2 kx squared. That's the potential energy. And state 2 is when the rocket has reached its maximum height. I've gotten rid of the other terms, the terms that go to zero, such as kinetic energy and gravitational potential energy in the case of 1. And so it just comes out to an equivalence between these. We're going to solve for k. K equals 2 times mass times g times the height divided by the spring compression squared. Here are all the values that we plug in. Make sure you do them in MKS units. So mass should be 65 times 10 to the negative 3rd kilograms. X should be 0.14 meters. And we get K of 2275 newtons per meter. Let's do that to two significant figures, so 2.3 kilonewtons per meter. Number 24. Particle slides on a frictionless track. Find its speed at B, its speed at C, and the approximate location of its right-hand turning point. All of these energies are the same. Energy at A, energy at B, energy at C, energy at the turning point. So we're going to equate whatever terms we need to answer the question at hand. So part A, it's appropriate to equate the energy at A equals the energy at B. So potential energy at A, mg times the height of A, equals energy at B, kinetic energy, 1/2 mvb squared, plus mg times the height at B. Notice how mass is a factor in every one of those terms, so let's divide each equation by mass. And so we have this term, or this equation. I've taken the square root of both sides, so we get the velocity at B is square root of 2g, and I factored that out, so times HA minus HB. When we plug in all those values, as you see here, we get the speed of B is 4.850 meters per second. So I've rounded it to 4.9 meters per second. To solve for part B, we are going to put the energy of A equals energy at C. And you go through the same algebra. It's just basically what I did for finding the energy at B. You can pretty much just change all these letters to the letter C, all these letters B to letter C. And so here you see the speed of C is the square root of 2g times HA minus HC. And that is 7.0 meters per second. For part C, the turning point is the point that has the same value, the same height as point A. You can look at the graph. Slip this in here. You can look at the graph and see where that is, and it's going to be about right here. If you put a nice ruler there with a horizontal line, you can see it happens at a position of about x equals 11 meters. Number 25. I recommend with a problem like this that you graph it. Either do a quick little sketch, do it on a graphing calculator if you have one available. It makes it much nicer to be able to see what's going on. The particle slides back and forth. Its position is y equals 0.92 x squared. And A is that 0.92. The particle's maximum speed is 8.5 meters per second. Find its turning points. Okay, so what I've done here, I didn't do it on a graphing calculator, but if you have an equation like this, you know it's going to be a parabola whose axis is at x equals 0. So the shape is going to be something like this. The turning points are going to be symmetric about x equals 0. And you should know that the maximum speed is going to be right down here. So here's what I've done. Here is state 1, where it's at a turning point. And it doesn't matter which turning point, they're going to be it's going to be symmetric, so whatever x we find here, it's going to be the opposite of that here. So I just went with the positive one. That's state 1. State 2 is at x equals 0, where it's got maximum speed. Energy at 1 equals energy at 2. I made appropriate terms go to 0. Kinetic energy at 1, because it's a turning point. Potential energy at 2, because that's a turning point. So we've got potential energy at 1 equals kinetic energy at 2. mgy1 equals 1/2 mv2 squared. Notice how the m's divide out. G times, and here I've made the substitution, instead of y1, let's call it 0.92 x squared. And that's the x that we're solving for, the turning point. Equals 1/2 times maximum velocity squared. You solve that for x, and it becomes plus or minus square root of maximum velocity squared divided by 2g times 0.92. And you should get plus or minus 0.20 meters. And that plus or minus is important because we expect that there are two turning points, as you can see in the picture. And so both of those are the answer. Number 26. The figure shows a particle's potential energy curve. Find the force on the particle at each of the labeled curve segments. All right, the bottom line here is you can see that formula at the top of your screen that force is equal to the negative of du dx, the derivative of position, which means it's going to be the negative of the slope. And as I wrote here, change in u over change in x. You can think of that as rise over run. That's what slope is. So what we're going to do for each of these problems is look at the curve, find a rise over run. That's what the force is going to be, or rather the force is going to be the negative of that. So for part A, the negative of change in potential energy over change in x. I've just looked at each of those line segments and I've taken, for example, for part A, the potential energy goes from 0 to 3, and the x value goes from 0 to 1.5. So I've done the final minus initial potential energy over final minus initial position. 3 minus 0 over 1.5 minus 0. Remember, we're taking the negative, that's what force is, so you get negative 2 newtons. Part B, potential energy doesn't change. Or you can look at that graph and see the slope is 0. It's horizontal, so we can expect force is going to be 0. Part C, the answer we get is positive 8 newtons. The slope is negative, and it's very steep negative, so what we can expect is that the force is going to be high and positive. Part D, it's negative but not as steep, and we get plus 1 newton. Part E, now the slope is positive, so we're going to expect a negative force because that little negative sign in the beginning. So you should get negative 4 newtons. And part F, just as with part B, it's horizontal, it's got a 0 slope, and therefore the force is 0. Number 27. This is another problem that it might be worthwhile to graph it, or at least do a quick sketch. We know that it's a parabola. The potential energy, the potential well is described by u of x equals 16x squared minus b, and then it says where b is 4 joules. So we'll just write that right there. Find the force on the particle. Okay, this goes back to the last problem where force is the negative of the derivative. And so when we take the derivative of ux, that's going to be 2 times 16, that's going to be 32x, but it's the negative, so force is going to be negative 32x. From here, we just take whatever x value it's asking and plug it in. So the force at 2.1 meters is going to be negative 32 times 2.1, we get negative 67 newtons. By the way, I've drawn that. Part A is somewhere up here, so it's going to be the negative of that very steep slope. Part B, x equals 0. Plug that into the equation, negative 32 times x, and that's going to be 0 newtons. That's right down here with a slope of 0. And when x is negative 1.4, that's somewhere here, it's got a very steep negative slope, and so it's going to be the opposite of that, so 45 newtons. Number 32, a carbon monoxide molecule can be modeled as a carbon atom and an oxygen atom connected by a spring. It gives the displacement from equilibrium. The potential energy increases by 0.015 electron volts. What's the spring constant? And if you're wondering what an electron volt is, look it up. It is in the front flap of the book. The conversions are given. Here's the conversion, 1.602 times 10 to the negative 19 joules per electron volt. So we're going to need to do that conversion because we need MKS units. So you should convert that to be 2.403 times 10 to the negative 21 joules. All right, once we know that, we can take this equation. Potential energy is 1/2 kx squared. Remember, even though it's not really a spring, it says it can be modeled like it. Mathematically, it works out very similar. So K equals 2u over x squared. And we get 1877, and we'll, with two significant figures, call that 1.9 kilonewtons per meter. Number 35. Number 35, the force exerted by an unusual spring when it's compressed is F equals negative, and I'll just give those numbers, negative 220x minus 3.1x cubed. So the change in potential energy, just standard formula, is the negative of the integral from initial position to final position of f dx. So we're going to take this integral. Negative, there are your limits of integration, and there's the force, negative 220x minus 3.1x cubed. Do that integral. So this becomes 110x squared. I've already taken the negative of the integral. So 110x squared plus, and I just left this so you can see what it is. It's 3.1 divided by 4 times x to the fourth. We take it from 0 to 0.15. Of course, you'll plug in the 0.15. Plugging in the 0 isn't going to subtract anything away. And you should get 2.5 joules. Number 37, a particle moves along the x-axis under the influence of that force. Find its potential energy as a function of position. So we start with F equals, there it is, ax squared plus b as given in the book. Potential energy is the negative of that integral, just as with the last problem. We're going to plug in, instead of f of x, we're going to actually plug in the ax squared plus b. Take that integral, remember the negative sign that's out front, and you should get negative 1/3 ax cubed minus bx, taken from 0 to x. Now when you plug in the 0, nothing's going to get subtracted, or 0 is going to get subtracted. And so the answer for potential energy is 1/3 ax cubed minus bx. Number 43. There's the two springs, one on the left, one on the right, and the red block going back and forth between them. The problem gives all the information. Find the maximum compression of the right-hand spring and the speed of the block as it moves between the springs. So let's call these state 1, where it's compressed against the left spring, state 2, where it's compressed against the right spring, and state 3, when it's speeding back and forth and the springs have no compression in them. Here are the k's, here's delta x. For part A, we want to solve for delta x at state 2. So conservation of energy, E1 equals E2. We think about what are the energies? Well, at state 1, it's 1/2 kx squared. Notice the subscripts that I do, 1/2 k1 x1 squared. You don't just want to put k and x because you have multiple k's and x's. You want to distinguish between them. So k1 x1 squared equals 1/2 k2 x2 squared. The halves divide out. And what we're left with a bit of algebra, is x2 equals x1 times the square root of k1 over k2. We plug in the numbers and get 16 centimeters times this ratio, and it becomes 10.9 centimeters. I'll round that to 11 centimeters. The next question asks, how fast is it going when it's in the middle? So we're going to set E3, that's the state of interest, to, we can do it either E1 or E2. Since we're given all the information for E1, let's go for that. However, you could set it equal to E2 as well. E3 is 1/2 mv squared equals 1/2 k1 x1 squared. And by the way, a good check could be, you could also say equals 1/2 k2 x2 squared, but I chose this way. So our maximum speed is plus or minus x1 times the square root of k1 over mass. Now the plus or minus just means it has two possibilities. It could be going to the right or it could be going to the left. But its speed as you solve for it is 4.1 meters per second. Here's a good check to make sure we did everything right. Down at the bottom of the screen, the amount of energy at any one of these states is a quantifiable, it's an amount, and it should be the same throughout. So if we take what we know, the energy at 1 is 1/2 k1x1 squared, we can actually plug in those numbers and get 1.66 joules. We should be able to take the answers that we got from the problem, such as E2 is 1/2 k2x2 squared, or E3 is 1/2 mv squared. We should be able to plug those answers in. They should come out to 1.66 joules, showing that energy is conserved. Number 48. All right. Number 48, a particle with energy 3.5 joules is trapped in a potential well, described by the equation. Find its turning points. All right, when you look at this equation, it's a quadratic equation. Hopefully you can see it's a parabola. You can graph the equation. That's a pretty neat thing to do. I haven't done it here, but recognize it's a parabola. The turning points are going to be where kinetic energy is equal to 0. Now remember that mechanical energy E, that 3.5 joules that it says, mechanical energy is kinetic plus potential. If kinetic is 0, then at the turning points you're solving for the condition where is potential energy equal to 3.5 joules? Where is it equal to total mechanical energy? So I'm going to set it up this way. Here's our equation for potential energy, and I'm going to set it equal to total energy, 3.5 joules. Because again, the kinetic energy is 0, so those have to be equal to each other. From this point forward, it's just algebra. What I've done here, I've turned it into a quadratic equation in standard form. Solve it for x. How do you solve for x? You can use the quadratic formula. You can, I think I graphed it. I did it in a graphing calculator and got 0.488 meters and 4.2175 meters. So I've rounded those to 0.49 and 4.2 meters. The final problem, number 58. A particle slides back and forth in a frictionless ball whose height is given by h equals 0.18 x squared. Find the x-coordinates of its turning point given a certain maximum speed. All right, here's my crude drawing of the bowl. It's a parabola. We can say E1 equals E2, where state 1 is the turning point. State 2 is the where it's got maximum speed at the bottom. I've drawn this red line just to show this is the total energy curve. So E1 equals E2, all right? The energy at 1 is mg height, equals the energy at 2 is 1/2 mv squared. When we solve for height, we get v squared over 2g. So that's the height right there, 0.01127. That is as high as it goes on either side. But the question is asking not what is the height, but what are the x values. So now we're going to plug in this definition given to the problem that the height is 0.18 x squared. And we're going to solve that for x. So we get x squared is 0.062613. When we take the square root of both sides, we get plus or minus. The plus or minus means over here or over here. Plus or minus 0.25 meters. Now, how can we check that? Well, we know that energy is conserved, so energy at state 1 should be equal to energy at state 2. We can say for energy at 1, mgh, and we plug that in. That's going to be mg 0.18 x squared. And so we plug it in. Now we don't know what mass is, but what we can get is that it's going to come out to 0.11 m. And then energy at 2, 1/2 mv squared, plug in those numbers, and we get 0.11 m. So regardless of what mass is, they come out to be the same. And that's the end of Chapter 7 homework.